Okay, so right now let's look at diffusivity, right? So where we'll be talking about the fixed first law, right? So let's see here. So the diffusivity, the unit is meter cube per second, right? So you should know the thermal diffusivity, which is in heat transfer. Then for momentum transfer, you talk about the kinematic or viscosity, right? So it's in terms of mass transfer, you're talking about the diffusivity, right? So yes, so we have diffusivity, right? So over here you can see that the diffusivity depends directly is indirectly proportional, right, to the pressure, which is where we are talking about up to 25 atmosphere, right? Then the for temperature is to the power 1.5 or 3 over 2, right? It's directly proportional to temperature in this form, right? So that we can evaluate the diffusivities at different temperatures, right? Then so this is the range of diffusivity values, right? So from here you can see that the diffusivity over here, right, at a certain temperature, right? Then over here you can see the diffusivity is being multiplied by what? The pressure. So when you report it is the ABP, right? Which actually the 2 points, let's say 0.006. So if I want to actually get the AB, it's actually that value divided by what? The pressure, right? So the pressure, that's the total pressure in the system that we are considering, right? It's actually down. So we always have to make sure and make sure this pressure too is in Pascal, because the unit of that is Pascal what per second, right? So you can actually get your answer. Yeah. So that's for that one. Then we can also see that we have ways, right? So when we have a non-polar or we have non-reacting molecules, we have a way to also estimate is what diffusivity. So one method that we can use is the what we call the Wikili method, right? So it is the Wikili method that we have over here, having the AB equal this one over here, right? So every term over here has to be evaluated in such a way that you can actually calculate for the AB for the non-polar or the non-reacting or molecules, right? So you can see how to calculate for the MAB, right? That's the what you call the molecular weight, right? So we have the average, right? So we estimate that one. We estimate the collision diameters, the diffusion collision integrals, right? And a way to evaluate all these things is that you need to also calculate what you call um the temperature, right? So the temperature that the T star over there is equal to the KT, right? Where all these things are being tabulated, right? So over here you can see that if you want to calculate for this one, you need to calculate for this T star, T asterisk, right, before you can actually get all these things, right? And all these things are also relations for us to get the weekly. So from the formula, based on the formula, we use all these small formulas to actually evaluate the terms in the weekly formula. Then we can just substitute them in there and do our calculation, sure. So this is where, in terms of when you don't have an experimental data, this is how you can calculate your collision diameter, right? Is this formula where the VB is the molar volume and TB over here is the normal boiling point, what? Normal boiling point, which is the temperature, of course. Right. So we have ways to evaluate all of those things, right? And if we have also what we call the Fuller method, which is also one way to also evaluate the diffusivity for non-polar or non-reacting what molecules. Yes. And when we talk about the multi-component, when we have a gas mixture, and we want to determine the diffusivity of one of the gases in that mixture, we use this formula where we call the diffusivity, right, in the mixture, right? So yeah. So let's look at some examples on how to evaluate them. Right. So as we can see, as we can see over here for the fourth question, right? You can see that we have oxygen A, right? Oxygen, which is A, right? A component A is diffusing through carbon monoxide, which is B, under steady state condition, right? With the carbon monoxide non-diffusing. So you are talking about a stationary, right? So the carbon monoxide is stationary, it's non-diffusing, right? And they give us the total pressure, the temperature, they give us the partial pressures of oxygen at the two planes, right? And the diffusivity for the mixture to they give to us. So they're asking us to calculate for the rate of what diffusion of oxygen. Right? So they want the rate of what diffusion, right? Which actually makes sense. You see from the Fick's law, right? When I have the total flux, you know that total flux becomes what you call the diffusive what flux, right? Plus the convective what flux. Right, and the diffusive flux part is where we have the where we have the fix, right? Fixed first law coming inside. So you have the C, the AB, right? Then you have the dy dz, right? Then over here becomes what we call the so this one over here is the convective what flux, right? So this is what you're coming to. So they want us to calculate for the rate of flux. So this is the rate of flux they want us to calculate for. So we need a diffusive flux and a convective flux, right? Where mostly, so since here you're considering two components, right? So you're considering A and B. Right, so you say that here is YA, so here becomes NA plus what NB. And since I was talking about steady state and carbon dioxide is non-diffusing, which is B, that means its flux becomes what? Zero, right? Because it's non-diffusing, so it becomes zero, which reduces this equation to this form. Right, so we have YAN, right? So I have to make NA the subject. So I have one NA over here. So if I bring it over here, I have this way, this AB, the Y, the Z. So that means that NA, so factorizing NA out, I'll be having this. So that means that my NA will be equal to I have minus C the AB over 1 minus YA dy dz, right? So this is what I have, right? But over here, I have to also do what we call I have to do my integration to just get the thing to remove the differentials from there, right? If I want to get rid of them, that means that I need some boundary conditions, right, to remove them. So I can say that at x1, right, at z equals z1, when the should I say it, when the thickness, right, is equal to z1, when the distance is equal to z1, right, y, right, y at that point, right, let's say becomes ya1, right, then at z equals z2, the y becomes what, ya2, right? Because you're talking about just the A over here, right? So that will help us in our differential, right? In breaking down this thing, right? So from there you can see that you can actually do the terms, right? In such a way that I have NA um dx will be equal to minus C dAB multiplied by 1 over 1 minus YA dy, right? So I take integral from here from YA1 to YA2. Then I take from here from Z1 to Z2. Alright, so doing this integration, I'll be getting Z2 minus Z1. That's for that place. Then by here minus CDAB. Right, so if I do my integration, right? If I do my integration, I'll be getting negative ln of y minus what? YA. Right, which I have to put in my limits YA1 to YA2, right? So I'm getting rid of that. So here becomes NA. So this change in z. So that change in z is what? Is the thickness or is the distance, right? The distance. So over here, yeah, which is the distance, right? So now this negative can take out this negative, right? So this one becomes C dAB, right? Then I can put in my length. Right? If I put in my lane, I'll be getting um lane of y minus ye2 over y minus ye1, right? So that becomes pretty much easier for us to actually get, right? So you see, you have to, when you get a certain situation, right? The overall is this one or this one. So depending on where we have a non-diffusing state or where we have equimolar diffusion, right? So you talk about the counter equimolar, right? So counter equimolar would mean that Na will be equal to minus what? Nb. We can also have a counter diffusion, which is not equimolar. That one, that means that they will give you a certain relationship that maybe Na relates to Nb, maybe 0.75 of Nb, right? That's not equimolar because you don't have one here. This is 0.75, right? So that's counter diffusion, but it's not equimolar. So you always build your equation from scratch. So it starts from here, and based on the system or based on the whether it's non-diffusing or it's equimolar, it's counter equimolar or it's just counter diffusion, right? Based on those things, you can be able to adjust your equation so that if you get your final answer, right, you work it from there. So you just put your values in there and calculate whatever you're supposed to calculate for, right? But over here, we can still make some assumptions, especially when we want to put in what we call the when we want to put in pressure. Right. So if I want to put in pressure, I know that my mole fraction is the partial pressure, right? So Y is partial pressure divided by the total pressure. Right. So I can have for one, right? I can have YE2, which is PA2 over P. Right. So I can bring that one too also into this formula. The P's can come out then. Yeah. And since you are using them in terms of pressure, mean that this concentration, right, would have to be in terms of this one. Like since you are bringing everything in terms of pressures, the concentration over here should be in P over at RT. Right, to make your this thing very easy for you to solve, right? Right now let's look at the question. So the question, right, gave us a DAB, right? So a DAB of 1.87 times 10 to the power minus 5 meters squared per second, right? So if I have this is my DAB, right? And they give me a total pressure of 1 times 10 to the power 5 Pascal, right? So and it said that the change in Z, right, is 2 millimeters apart, right, which is 0.002 meters, right? That's the change in Z, right? And so if that's a change in Z, and they gave me the partial pressures at 2 points, do you get it? So the partial pressure for oxygen, so you know that oxygen at point 1, right, becomes um 13,000 Pascal, right, and oxygen at point 2 becomes 6,500 watts Pascal. Right, so I have um, that's for oxygen, yeah, which is E. So the partial pressures was giving us that, right? So if I have all these things over there, that means I can use this equation. I have Na, right, which is the AB times P over RT times the change in Z times logarithmic mean of the pressure, right? So this one multiplied by PA1 minus what? PA2. And, this one is much easier for you to solve, right? Where that PB, the logarithmic mean, right, becomes PB1 minus PB2 divided by ln of PB1 over PB2, right? So this actually gives me that value, right? And for me to, so over here I have A1 and A2, right? But I need, so I can see that PB1, right, will be the total pressure minus the PA1. The total pressure is 10 raised to the power 5 minus 13,000, right? So this one gives me a pressure of 87, right? So this one gives me 87, kPa, right? Then PB2, which will be the total pressure times your power 5 minus PA2, 6,500. That gives me 93 kPa. It's 93 kPa. So if I get this one, that means I can calculate the log mean, right? So I'll have 87 minus 93, all times here is your power 3 because they're in kilopascals. Then ln of 87 over 93, right? Over 93. Yeah, so over here, the log mean, right, will end up getting 9,29022 Pascal, right? That's the log mean. So if I have the log mean over here, meaning as I can go back to my question here, right? If you don't want to use this one, you can use the one with the move fraction. Just that that one is long because you have to be calculating your P over P. I mean the partial pressure divided by the total pressure to get your y. You come and put it over there. That one also works, but this is just a simplified form for us to just use the parameters in the question to actually evaluate whatever you want to do. So based on this one, NA becomes the AB is 1.87 times 10 to the power minus 5. Then the total pressure is 10 to the power 5. Then divided by, so here is 8314 times 273. That's the temperature, right? That's 0 degrees Celsius. So in terms of Kelvin, I have that one. And the constant, I also have that one times 0.002 by um PB. So that one becomes 90.2 times 10 to the power 3. I mean, the value I had over the log mean. So this one also multiplies by, so PA1 is 13 minus 6.5 all times 10 to the power 3. I mean, tens of kilopascals, right? So Na becomes 2.97 times 10 raised to the power minus 5 kilomole per meter square second. Right, kilomole per meter square second. But the question said that they want the rate, calculate the rate of diffusion of oxygen in kilomole per meter second through each square meter of the two planes, right? So square meter each. So just one, right? So that means that if I have just 1 meter squared, right, the answer becomes 10 to the power minus 5 kilomole per second, right? So I have my answer now. So this is the part the question wants. So we build it from scratch. Right, so you can actually use the equation that we ended up with. So the Na was equal to C the AB over change in Z ln of 1 minus Ya2 over 1 minus Ya1. So you actually have to get this one using your total pressure. Right, so you use P over RT. So you can use that one to get the concentration. You have the AB, you have this one, and Ya2 and Ya1 will be much easier to get. So your Ia1 will be like Pa1, right, divided by P. Then your Ya2 will be Pa2 divided by P. So if you get these ones, you can just put them over here and just do that one. So that one also works, right? Any of them, just that this one, since we are giving pressures, we wanted to just put them in there and use that. That's why we use the simplified form of it, right? But any way you get to that, you can use, then you do that here. And the fifth question, right, is telling us that we should recalculate the rate of diffusion for A, right? Assuming the non-diffusing gas is a mixture, right? So right now you can see that we are having a mixture of gases, which is methane and what, hydrogen, right? But they said it's in a volume ratio of what, 2:1, and they gave me the divisivities of oxygen in hydrogen and oxygen in methane. Right, so over here we have to recalculate our DAB. That's the only difference that will be over here. Just calculating DAB. Right, everything will still be the same, but we're calculating the AB, right, in such a way that we want to find the diffusivity of A in the mixture. Yeah, because right now you see the non-diffusing is a mixture of what methane and what hydrogen, right? So if I want to get that one, it becomes the A in terms of the mixture becomes 1 divided by, so we have YB, right, divided by the ABR plus the YC, which is for the hydrogen, also divided by is what the so this one will be the AC, right? So this is the AB, A in methane, then A in what? The hydrogen, right? But we need to get YB prime and YC prime, right? So YB prime, so they gave us the ratio, right, which is 2 over 2 plus 1, right, which is 2 on 3, right, which is 2 on 3, which gives me a value of 0.667. Then the YC prime becomes 1 over 3, which is 0.333. Right, so that will help me to get my diffusivity of the oxygen in the mixture. Right, so it becomes 1 divided by, so over here I have, so always this is how you have to do it. You always have to make sure you find the diffusivity of the gas you want in the mixture. So if it's oxygen, the bottom here should be the diffusivity of oxygen in one of the gases and diffusivity of oxygen in the other gas, right? We can have the mixture to be maybe 3 gases, so you can also add another one, but just make sure you be able to calculate these ones that you have over here, right? Sometimes they can give you more fractions, right? So you just use that one to calculate for these ones. But here becomes 0.667 divided by, so the AB was given as 6.99. Alright, the AB, so in terms of and methane, oxygen in methane is 1.6, right? So 1.86 times 10 to the power minus 5 plus 0.333 over 6.99 times 10 to the power times 10 to the power minus 5 t. Right, so that gives me the diffusivity of A in the mixture, and that gives the diffusivity of A in the mixture to be 2.46 times 10 raised to the power minus 5 meters squared per second. Right. So if I get this one, I can actually recalculate my what, the AB. So I can actually recalculate my NA. So my NA now becomes, so it's just the AB that will change, which is 2.46, right? Times 10 to the power minus 5 multiplied by 10 to the power 5, which is the pressure, then 13 minus 6.5 times 10 to the power 3, all divided by 8314 times 273 times 0.002 times 90.2 times 10 to the power 3. That's the log mean, right? That's the log pressure mean over there. So having this value can actually calculate for my flux, right? So plus 10 to the power minus 5, right, multiplied by 10 to the power 5 multiplied by 13 minus 6.5, also times that one times 10 raised to the power 3, right, divided by 8314 times 273 times 0.002 times 90.2 times 10 raised to the power 3. Right, so that gives me an Na of 0.0000039, is which is 3.9 times 10 to the power minus 5 kilomole per meter square second. So per meter cube, right? So per meter squared. So this one, the meter square can go out and we will have just in terms of what kilomole per second, right? So that's it. So when you have a mixture, that's how to calculate for the diffusivity, right? So this same question, you can have it in such a way that they will tell you that we are having so based on the equation that I build from the top. So NA equal minus C dAB dy dz, right? So I have plus, so YA NA plus what? NB. So it can be that you have equimolar counter diffusion, which is something like this. So that means that the flux of A is negative of, so it's counter equimolar. I should have the same composition 1 1. Right. So this one for here, it becomes Na becomes minus C dAB dy dz, right? Then plus here becomes YA, here becomes Na. Then the NB becomes minus Na. In such a way that this side goes away. So that's the most simplest one when you are trying to solve divisibility for this kind of questions, right? So the Na becomes minus C dAB, then dy dz, right? So as we have for that same thing, right? When we have limits, right? We can have limits. Right? So over here, I'll be having Na. So if the dz comes over here, I'll be getting change in z because I'll integrate from z1 to z2. Right? Then here too, I'll be having minus C dAB. Right? So over here too, I'll integrate. Right? So I get y1 minus y1. Right? Let's say this y. Yeah. Yeah. So this is what you'll be getting. So this is also the simplest one, right? Yeah, it is very, very simple. So over here too, if we want it in terms of pressure, you know what to put over here, right? You know what to put over here. So here becomes the PA2 over P. Then here becomes what? PA1 over P. Right? Then the concentration, right, will change to P over what? RT. And then so this is the most simplest one we are solving for counter equimolar counter diffusion, right? But what if it's not equimolar counter diffusion? Right? What if it's not equimolar? So the Na becomes minus C dAB dy dz plus, so we have this, right? And over here, it's not only two gases that you can have diffusing. Sometimes you can have three gases that are diffusing, right? So that one to here convection, the convective flux, that part, right, will be changing a lot, right? But I can say that MB is equal to 0.75 over MB, right? Yeah, I can. Yeah, I can say it this way, right? Where, but since this one is in terms of Na, everything over here should be in terms of Na. Right? So the AB, the Y, the Z plus. So here will be YA. So I'll replace just the NB. So if I'm replacing NB, right, NB will be what? Na divided by 0.75, right? Which I can work around. So I have Na minus C dAB dy dz, and plus over here, I'll have so I have 1 plus 1 divided by 0.75, which is 2.33, right? So here I have 0. So I have 2.333 YANA. Right. So if I shift this one to this side, now factor it, I'll get Na 1 minus 2.333 YA. Right. So it should be equal to minus C dAB dy dz, right? And so over here, Na times change in Z. So when the Z comes over here, I integrate from Z1 to Z2. This is what I'll get. Then I'll have C dAB. So here I'll be having dy divided by 1 minus 2.333, right? Y. So if that side, I do my integration, right, for I do integration for this side, right, I'll be ending up with minus 1 over 2.333 ln of 1 minus 2.333 YA. Then so I'll integrate from YA1 to what YA2, so I'll put in the limit. So that is what I'll get to. It always depends on whatever you are getting. The rest becomes math, calculus. You just have to be able to solve your integration without what a problem. So here I was integrating from y1 to what y2. So you just have to be able to solve all these questions, right? Based on the kind of system that you are having, right? Yes. Well, let's go back here. Yes, let's go back here and see something here. Yes, over here. This is what I was talking about. When you have a stagnant film, so the one we talked about when the one was non-diffusing, right? And if you have also have you can also have diffusivity in liquids, right? Which that one too you can also actually evaluate. So this is the accumular counter diffusion, right? So we have this one. And when you have an ideal gas situation and you are bringing in the P over RT, right? Yeah, it can be simplified for you to do it. Yes. And so the next thing we're talking about over here is the evaporation of a spherical what, droplet. And so you have a spherical droplet. This is how the thing behaves, right? So you assume the air is to be stagnant because you have if you have a droplet and you have a large mass of air around it, you assume the air around it to be stagnant, right? Which that means that NB becomes zero. But over here, since we are talking about a spherical thing, we talk about the radius, not the thickness or the distance, not the z, right? So that's the only difference that comes over here. And the boundary conditions too might also change, right? The boundary conditions might also change. So you try to solve for that one, and yeah, this equation is also very, very important, right? So this is the initial flux, right? And having to solve for this one, right? So if you solve for everything, right? This is the equation we'll end up with. So we'll be ending up with um we're ending up with so if you have initial conditions and all those. So this is the equation I end up with. So this is the time, right? This is the time we can use to calculate for it. So everything started from the top. So if you know what you are doing from the top, then you'll be good to go, right? You'll be good to go. The integrations and all those things, right? To be and you have the combustion, right? We have a combustible situation. We also evaluate that one as if you are doing the droplets, right? So that one also becomes a certain case that we can. And diffusion in liquids, right? That one too, this is how we have it. So for a steady state, right? When we have a B to be non-diffusing, this is how it will behave. The only thing that changes with this one becomes the concentration. It becomes rho over m average, right? That's the only thing that changes with the liquid, apart from the with respect to the gas, right? That's the only thing. The concentration, how to evaluate the concentration. That's the term that changes when find diffusivity for a liquid, right? And then you have accumular to we model it the same as doing for a gas, but it's only the concentration side that changes to that formula. Yes, that changes to yeah that formula. Yes. Yes. Thank you.